Hello everyone, this is Mr. Sen. Welcome back to my YouTube channel. In today's video, I'll be looking at how to determine the potential energy of a mass that has been hung on a spring. So before we even continue with the video, don't forget to like and subscribe to this channel. Alright, let's get to it and see how best we can understand. So now, potential energy isn't actually a difficult thing to understand. As we all know, energy just talks about the ability that we have to do work. Our capacity to work is energy. As we mostly all know, potential energy is just the energy that the body has as a result of its position. Alright, with this said in mind, let's try and look at the conditions we might be given under Hooke's law that relates to the deformation of solids. So suppose we have condition A. Condition A, let's take it to be a condition where we just have, let's say, a fixed support here. Let's say fixed support. And we're having a spring without anything attached to it. So this spring will have the initial length, which is length initial. But now what you have to understand is this. Due to the fact that there isn't any mass attached to this spring, because as you see here, this only has an extended length. So there's no extension. So if we were to find the potential energy in condition A, we know potential energy is mass gravity times what? Height. Here the height is length initial. So even if we say potential energy is equal to mgl initial, we don't really have mg because there's nothing attached to this spring. So if the potential energy has no mass, which provides the weight if we consider the mass due to gravity, then we'll have the potential energy of this condition A to be equivalent to 0 at joules. So in condition A, the potential energy is literally 0 due to the fact that there isn't any mass attached to it. If we consider condition B, now in condition B we might have a fixed support, as we all know. Suppose a mass has been now attached to this spring, it's going to cause an extension. So this is the mass. Now mass acting against gravity creates a force which we call weight, which is equivalent to mass times gravity. So there's this extended length, which is length final. Let me say length final 1. So if we want to calculate the potential energy in this condition, we will say potential energy is equal to mgh. Now, due to the fact that the height is now the final length, we just say mg what? Length final 1 that we have here. So this formula gives you the potential energy of a system that's been put in condition B. So here we only have one force acting on this system, which is force what? F. So be mindful of this. So the potential energy will be this. With this in mind, we can now look at a different condition that we might have. So suppose we have a condition as C. Let's say condition C. In condition C, let's say we have a support like that, and then not only a mass has been hung, but also another force is applied to it, creating a different type of extension. So we're having force, let's call this another force, force F, and we also have the other force, which is gravity, mg. Length final is this. So to calculate the potential energies in condition C, we know a potential energy is equal to mass gravity times what? Height. So potential energy is equal to what? mg LF. Let me call this LF2. Now here we're trying to look at the potential energy that has been created by the mass. The keyword is to understand that here we're trying to focus on the mass. Okay? The mass that has been attached to the spring. Yes, the force is there creating a different extension, but our interest is the mass that has been attached to the spring. Now, with this in mind, we now understand how we can determine the potential energy in condition B and what? C. But now, what if we were asked to find the change in the potential energy of the mass due to the extension of LF1 and LF2? If we are taught to find the change in potential energy of the same mass due to the extension of LF1 and LF2, what would happen? That change in potential energy will be the difference in the potential energy of condition C and condition B. Therefore, we would say potential energy 2 minus potential energy 1. The potential energy that we're looking at here, the change in potential energy that we're trying to find here, will be equivalent to the potential energy 2, which is actually this one here. So we say mglf 2 minus the potential energy here, which will be mglf 1. This equation gives us a change in potential energy of the mass that has been hung on a spring. Now, this is basically easily understood if we consider different examples that relate to this nature. So let's try and look at the examples that we might come across under this condition. Okay, but be mindful that the potential energy is the energy that the body will have due to its position. Let's try and look at an example. Say you are having a spring of an extended length of 10.5 centimeters. It is suspended vertically from a fixed point, as you can see, fixed point as shown below. Now, a mass that has a weight of 2.5 is hung on a spring. This mass is now being hung on a spring. To change the length to 15.2 centimeters, again we have an additional force F, which is added, and it extends the spring to a length of 20.0 centimeters, as you can see it being shown here. Now, I've been asked to calculate, or they're saying for the extension of 15.2, this extension here, 15.2, calculate the potential energy of the mass on the spring. So now, how are we going to go about this? Let me just cut this part. Let me cut it somewhere here and see how best we can solve this. So let's just say solutions. So to find the potential energy, we know that potential energy is equivalent to mass squared times height, isn't it? So now the mass for the extension of 15.2 centimeters multiplied by the gravity gives us the weight that we have here, which is 2.7. So we know that potential energy can also be equivalent to the weight times the height, because the weight is the type of force. So potential energy is equal to the force, which is 2.7, times the height. Now the height will be considered to be the extension that we have, which is length final. So potential energy is equal to 2.7 times length final, which is for 15.2. Now this is in centimeters. You want this not to be in centimeters, you want it to be in in meters. So now what are you going to do? You divide by 100, isn't it? So you can just multiply by 10 to the minus 2, because 10 to the minus 2 is like 15.2 divided by 100, which is one and the same thing. If you compute this, you have the potential energy to be equivalent to yes, 0.4104 joules. Therefore, I can conclude, if I round off, to say my potential energy is 0.41 joules, and that will be our potential energy for the extension of 15.2 centimeters. I hope it's clear. The potential energy we're trying to determine, remember, is for the mass that has been attached to the spring. In short, it is for the load in this system that we have here. Be mindful of that. Now let's look at a different question that is similar to this. The question is the same, but it's B. It says for the extension of 20 2.0 centimeters. Calculate the potential energy. So we'll be doing the same thing we did in the previous example. So this is solutions. So we know potential energy is equal to mg what h, and we know the potential energy can now be equivalent to the weight times what, the height. But now the height for the extension of 20.0, that extension is the height. So we say potential energy is equal to the weight times length what, final. So potential energy is equal to the weight that you have, which is what, 2.7, times length final, which is going to be 20. Now it's in centimeters. You need to divide it by 100 in order for it to convert it to meters, or you can just say times 10 to the minus 2. So the potential energy, if you compute this on your calculator, will simply be 0.54 joules. As simple as it is. Let's look at the last part of this example. Now here we've been asked to say, for the extension of the spring from a length of 15.2 centimeters to 20.0 centimeters, calculate the change in potential energy. Now, change in potential energy is as a result of two extensions. So change in potential energy will simply be mg times the change in what? Height. Because we're looking for the change in potential energy of the mass. So what will only change are the final what? Lengths. Because we're trying to consider the potential energy here compared to the potential energy there. So now what is the difference in this potential energy to that potential energy? So it's a change in potential energy is equal to mg change in what? Length final. So you can say, okay, change in potential energy is equal to mg, which is the what, times length final, which is length final 2, minus length final at 1. So I can say change in potential energy is equal to the weight times length final 2, minus length final at 1. So change in potential energy is equal to what? What is the weight? The weight is 2.5 because our interest is the potential energy created by the load. Now, what is the first length? What is the final length final that we have in the system? Because in condition B, this is length final 1, but our interest is length final 2 minus length final 1. This is length final 2. So you can say, okay, 20 divided by 100, or times 10 to the minus 2, minus 15.2 minus what? Divided by 100, sorry. So what are you going to have when you compute this? You'll be having change in potential energy to be equal to 2.7. That would be, if you divide this, it will give you 0.2 minus, this is going to be 0.152. So the change in potential energy will now be 2.7 times 0.048. And the change in potential energy will now be equivalent to 0.1296 joules. So therefore we could say the change in potential energy is equal to what? Yes, 0.13 joules. And that is simply the change in potential energy. Or one could say change in potential energy is equal to potential energy 2 minus potential energy what? 1. This is potential energy 2, and this is potential energy what? 1. If you recall from what we did find, the change in potential energy in our previous examples, potential energy 2 was found to be 0.54 minus potential energy 1, which was 0.4104, and the change in potential energy of these two is equivalent to 0.1296 joules. And this is now what we're saying to say, okay, the change in potential energy is now just equivalent to 0.3 joules. So basically, going about this is very, very simple. The questions would come where they ask you to say, okay, find the potential energy of the mass that has been hung on that spring, which is the load. That's their most interest. And so going about solving that, we have actually explained in this video. All right. Be mindful that potential energy is just the energy that the body will possess due to its position or configuration. Thanks for watching. If you have questions, kindly contact me on WhatsApp on the number that is on top of the top left corner where there is Engineer Hossein WhatsApp and then that contact. Or you can use the number that I'll put in my description. Thanks for watching. My name is Mr. Hossein Mwasapi. Remember, it's very important to strategize before you become a statistic. And let's try to get that A+.